Okay, so here's the last multi-part question, sort of free response question on the practice final. I can't promise there's going to be exactly 4 on the actual final, but I think the range I gave on the study guide was 4 or 5, so it's going to be close to this. I just might have 5, and maybe a couple of them won't be quite as long as these or whatever. In any case, this one is a question on our AM radio receiver. This is something that is the newest material in the course, okay, and is pretty tricky because we're putting together a lot of different circuit elements than we're used to dealing with. And although we went through with our lecture videos and talked them all over in some detail, it can be difficult to absorb on a short time scale. So that's why I wanted to go over this one in pretty carefully. Okay, so this may be a slightly longer video. We'll see how it comes out. All right, so we've got our AM radio receiver. It's identical to the one that we were looking at in class. And in part A, what is the function of the combination of circuit elements within the dotted box? And then explain briefly. All right. So inside the dotted box here, we've got a diode, and that is usually referred to in this kind of receiver as a detector, but you could also call it a demodulator if you like. You may hear a plumber working on replacing our water heater. It went out this week, which added to the adventure of the quarantine. Anyway, so diode is a detector or demodulator, and that's what it does, okay? We'll talk a little more detail in a moment. Now, these two elements here work together as a filter. Remember that this RC combination is a filter that gets rid of the high frequency carrier wave. All right. Now, actually close this window. There we go. All right. So part A, what is the function of the okay? Well, we've already talked a little bit about it. Okay, so the diode that we've talked about, that chops off one polarity of the signal. So in other words, what it does is it, straighter here, it takes a signal that's coming to it that looks like, this, something like that. And it translates it to something that looks just like, and I don't know how well I'm going to be able to replicate what I had over there, but it chops off the negative polarity, right? And the reason why this is important is if you look at the amplitude modulation on this, so I tried to make it symmetric around the axis, but I didn't quite manage it. But in reality, it would be, okay? So if I look at it like that, okay? When you've got a big positive voltage, on average, if you're just looking at the envelope, there's an equal negative voltage. And so if you sent this whole thing to the speaker, then they'd essentially cancel out. And that is a problem, right? If you send 2 different voltages, assuming that we've filtered out all the high frequency stuff, because if you include that, then first it's positive, then it's negative, then it's positive, and then it's negative. But really, really, really fast, right? Faster than the speaker can really respond. And so we filter all that stuff out. But if we didn't chop off the bottom, then we'd have 0 net voltage being sent to the speaker, and so the speaker wouldn't respond. It just wouldn't create a sound wave. So we need to get rid of the bottom bit, and so when we send our resulting filtered audio signal off to the speaker, then we've got something that just has a variation in, say, positive voltage, and thus positive current in one direction, going up and down and up and down and up and down, and so the speaker will vibrate and create sound waves. Now, for the other bit, so for the RC combo, that's filter. It's what's called a, well, depending on how you interpret it, but it allows the high frequency stuff part of the signal, so high frequency carrier signal, to pass through and go to ground before going to speaker. Okay. And you can explain this a couple of different ways, but one way is to remember that the reactance of, so sort of the apparent resistance of a capacitor is, I think it's this. So it's inversely proportional to the frequency. So the high frequency carrier wave, so high frequency, low apparent resistance, high frequency part of the wave, the carrier wave, sees very little resistance in this branch of the circuit. And because it sees very little resistance in that branch of the circuit, it just comes to the diode and immediately goes to ground. Okay. Now, if you're thinking about the audio, much lower frequency part of the signal, well, it sees, so low frequency, high apparent resistance, so it would see a high resistance in this branch with the capacitor, so it would choose, mostly, to go off this direction. Generally, this resistor right here is a very high value as well, and so the speaker is where most of the power of the audio, low frequency stuff goes, and then goes to ground, rather than shortcutting that like the high frequency stuff does. All right, so that's one way of interpreting it, and there was another one. If that sort of explanation isn't working for you too well, there's another explanation that I put in the video on this subject on YouTube. All right, so for part B, we know that around here in most places on Earth, many different AM carrier waves, etc., etc., etc. Why is it that the audio information from only one carrier wave is sent to the speaker? Okay, so this part of the question is asking about the tuner, the LC combination. Remember, that's an inductor, that's a variable capacitor, okay? And there's a long and a short explanation for this, okay? But the short version here that I'll write out is that the LC combo has a resonant frequency, an F0, equal to 1 over 2 pi square root of LC, I believe. You can check your equation sheet and check my memory there. Has a resonant frequency dependent on these two LC, these two values, the inductance and the capacitance of the inductor and the capacitor up there in the diagram. And only signals that correspond to the resonant frequency, here, that was a little messy, resonant frequency will pass to the rest of the circuit. And all others see a low impedance or apparent resistance from the LC combo, the tuner, and pass directly to ground. Okay. And we talked a little bit about how that resonant frequency expression comes about. We didn't derive its form, but we talked about how if you were to separate this from this circuit and you were to charge up the capacitor and you were to just watch what happens in terms of the current and voltage here, you would get this oscillation in energy. It's part of the reason why sometimes it's called a tank circuit, It's like water, the energy in the circuit is kind of like water sloshing back and forth in a tank. So you've got first energy stored in the capacitor that causes current to flow through here, which at first gets opposed by the inductor, which limits the rate at which it comes off of the capacitor. But eventually the capacitor runs out of energy, and then the inductor here, tries to prop up the current that was going through it. And so it drives current in the circuit, and it and the effect of that is to recharge the capacitor, albeit with the opposite polarity of voltage it had when we started the process. And then that drives current back the other way once this thing runs out of energy, right? No more current flowing for a moment, and this thing is all charged up. And the current comes back the other way, and the whole process happens in reverse. And so that oscillation in energy from the electric field of the capacitor, that sort of separation of charge, to the magnetic field of the inductor caused by the current going through it, that oscillation of energy goes back and forth and back and forth and back and forth at this resonant frequency. And so if you try to actually drive, like power the LC combination with an AC signal, like comes in, like what is coming in on the antenna here, well then if the signal coming in corresponds to the resonant frequency, well then what happens here is that AC signal sees a really large impedance here, okay, from that combination. And so that signal that corresponds to the resonant frequency of this LC combination in the tuner goes off and gets detected and filtered and heard on the speaker, whereas all the other AC signals that are induced on the antenna from the passing electromagnetic waves, well, they see a much lower impedance here, a much lower apparent resistance, and so they just shoot through to ground, or at least most of their power does, and so you don't generally hear them on the speaker. Okay, so that's the idea. Okay, and that's the end of question 4. Sorry for the long-winded explanation, but I wanted to go back over a lot of things. But as far as how to answer these 2 questions for the exam, something like what you're seeing here on the page would do a pretty good job of getting you the 6 points total for this question. All right, so thanks for your attention. I'll be back for one more video where we'll quickly go through all of the multiple choice and short answer stuff on the practice final exam, and then happy studying. Hope it's going well.